So now let's talk about the law of conservation of energy. So in words, energy is neither created nor destroyed, it just changes forms. So we're going to do a lot of changing forms, but in this class we only really talk about three kinds of energy. We have kinetic energy, energy of motion. So if you're moving, you have kinetic energy. If you're stopped, you don't. And there's no direction. You cannot have negative kinetic energy. You can't have negative mass. You can't have F(g) squared, a negative number. Then we have gravitational potential energy, mgy. This is the energy an object of some mass has because of its height above the ground. Remember, that's why we use the letter y, because it's the vertical distance above the ground. It's not the path you take, it's how high you are, how far you could fall. And then we have spring potential energy, 1/2 kx squared. So this doesn't depend on the mass of the object. It depends on how far you compress the spring and how stiff that spring is. So the higher the value of the spring constant, the more energy you can store for the same compression distance. Remember, this is a lowercase k and this is an uppercase K for kinetic energy. Don't get those mixed up. And we can put these three together and we call this mechanical energy. Energy is always conserved. Mechanical energy is not always conserved. With mechanical energy, if you have outside forces doing work, then this will change because work changes energy. But the thing doing the work had to get its energy from someplace, so the energy of the universe is constant. We can add or subtract it to the system, but we're not going to do that on these first couple of problems. So, if no work is done on a system, it's mechanical. Yes, that's the proper is. It's, you put a apostrophe only if it's it is contraction. Its mechanical energy is constant. So we could start with kinetic and change in gravitational potential. It could start with spring potential and change into gravitational potential. It could start with any of these. It could start with all three of these in a rather contrived problem and change into just one. Last year I had to do two charts. So you had location, kinetic, potential, and mechanical. And so I might give you a problem where an object starts from rest at the top of a hill, and I want to know how fast moving at the bottom of the hill. So you said, okay, it starts from rest, it doesn't have any kinetic. I would give you the mass and the height. You would calculate some number here, and you would say, so the total mechanical energy is whatever that is. You would add them together. Well, then that had to stay the same, and then you worked backwards. How fast moving at the bottom of the hill? We're at the bottom, there's no height anymore, so this is 0. So that would let you figure out the kinetic energy at the bottom of the hill. Now, that's kind of clunky. I really like that for first year physics, but for second year physics, we're going to skip ahead. If the mechanical energy is constant, instead of saying these added together give you this, which is equal to this, which has to be equal to here, we're just going to use kinetic plus potential equals kinetic plus potential. And you'll just have to be aware of when you have to do what kind of potential. So this is how I'm going to do the example problems today. So first example problem. We have a flat surface that then curves upward. Nice pretty curve. And we have a spring right here. This has a spring constant of 500 newtons per meter. And then we have a block. It's not attached to the spring, but it pushes back. We're going to push it back 0.1 meters. The mass of this block is 0.5 kilograms. So we're going to push back the block and then we're going to release it. It's going to leave the spring and it's going to be moving pretty fast, and then it's going to slow down and it's going to reach some maximum height, and then it'll go back down. So I have two questions. The first question is, how fast is it moving right when it leaves the spring? So you need to always, for every problem, Identify your two locations, your left location, your right location. How fast when it leaves the spring? Well, I know information about before it leaves the spring. So on the left side, I have before it leaves the spring. And on my right side, I'm going to have my question. My second location is right after it leaves the spring. And I forgot to say this, but this whole thing is frictionless. So we don't lose any energy to friction. Conservation of mechanical energy holds. Before it leaves the spring, there is no kinetic energy because it's not moving. There is spring potential energy. There's no gravitational potential energy because it's at the bottom. So this is my only form of energy before it leaves the spring. After it leaves the spring, you know what? I'm going to write this out differently. I'm going to write all three. K plus US plus UG. It's not moving, and it's at the bottom. After it leaves the spring, it's moving, but it's not touching the spring anymore, and it's still at the bottom. And now I can substitute in my expressions. 1/2 kx squared equals 1/2 mv squared. And we are looking for the final velocity. So the 1/2 cancels. I'm going to divide both sides by m and take the square root. So v equals kx squared divided by m. Take the square root of the whole thing. Yes, you could take that out. I'm not going to deal with it. So we have 500.1 squared, all divided by 0.5. And so when I plug that into my handy dandy calculator, 500 times 0.1 squared divided by 0.5, then take the square root. I'm going to get that it leaves the spring at 3.16 meters per second. Oops, not quite all on the screen, sorry about that. So now I have a second question. I want to know how high it goes. So above the table, it's going to reach some maximum height, and then it's going to come back down. So I want to know what that height is. So I have a choice. Because this is friction, no energy has ever been lost. Since we just found how fast it's moving at the bottom, you could make your two locations after it leaves the spring and maximum height. And so if you did that, after spring equals, and then max height, well, after it leaves the spring, it only has kinetic. At maximum height, let's write them all out. Maximum height, it's at the maximum height because it's stopped. It's not moving. It does have a height, so we have UG, but this is US, it's not touching a spring, so it doesn't matter. So we'd write the kinetic energy, 1/2 mv squared, equals the spring gravitational potential energy, mgy. Notice the mass cancels out. And you could solve this. Or we could go back to the beginning, before leaves spring. Max height. If no energy is lost, no energy lost. You can go from the very, very beginning to the very, very end. So we'd have only spring potential energy and only gravitational potential energy. 1/2 little k x squared equals mgy. You can plug numbers in here, and you're going to find that y equals 0.510 meters. Or you can plug in numbers here, and you're going to get the same answer. So there are sometimes multiple ways to solve these problems. It's kind of how they're chosen. But in general, you need to pick a location where you know everything. And you need to pick a location where you're being asked about. So as a separate question with a little bit of trig involved, we have a pendulum. So remember, a pendulum is like the ball underneath the string, and it's going to swing back and forth. And I want to know, how fast is it moving at the very bottom? So for this particular swing, we are going to release it at an angle of 20 degrees from the vertical. So we're pulling it back 20 degrees and letting it go. The string is 1.5 meters long, and this is a 0.2 kg object on the bottom of the swing. So when we're looking for this V, we need to think about what kind of energies do we have. So at our pullback location, so farthest pulled back, we know it's not moving because we're releasing it, and it's some height, and we'll talk about that more in a minute, but it's some height above the bottom because we've pulled it back. It's moved up a little bit. So it's some height above the bottom. There are no springs in this problem at all. So if we do K plus US plus UG, released from rest, no springs, we only have gravitational potential energy. And then we're looking for how fast it bottomed. So at the bottom, we're going to set that as our 0 height point. So when we do K plus US plus UG, if I measure my height from there, then there's no potential energy. And of course there's no spring. So this is an MGY equals 1/2 K, or excuse me, 1/2 MV squared problem. So I didn't really need to tell you the mass because it cancels out. The height is not 1.5 meters. The string is always 1.5 meters long. So it's 1.5 meters long here, and it's 1.5 meters long here. We need the height. That's the vertical distance. That's the distance between these 2 points. So this is the y we need to plug into this equation. So this is 1.5, and this total is 1.5 meters. And we know this angle is 20 degrees. So if we're looking for y, we need to calculate the length of this part of the triangle. So I am going to call that, I'm going to make up another letter, let's call that z, just because we're already using x and y. So z. I have a triangle, it's a right triangle, because this is vertical and this is horizontal, just the way I drew it. So I need to pick a trig function. So for those of you who do not remember as well how to do this, so katoa, for 20 degrees, I have the hypotenuse because it's opposite the 90-degree angle, and I have the leg adjacent to. This is opposite, this is adjacent, it's right next to it. So I'm looking for adjacent, I know the hypotenuse. Adjacent and hypotenuse is the cosine function. So the cosine of 20 degrees equals adjacent z over hypotenuse 1.5 meters. So z equals 1.5 times the cosine of 20 degrees. 1.5 cosine 20. So z equals 1.40954. I'm going to keep lots of digits. So if this is z, y must be 1.5 meters minus z. So if I do 1.4, and I'm actually going to 1.5 minus, I'm going to use my whole calculator screen. I get 0.904610688 meters. And remember, because you're putting your numbers into Schoology, keep the whole thing. You don't have to write the whole thing down. You can keep it on your calculator screen, but I find this helpful. So to finish this problem, remember we did most of the energy analysis back up here. To get v by itself, I need to multiply by 2 and take the square root. So v equals the square root of 2gy. So 2, 9.8 times this whole thing. So in my calculator, times 2 times 9.8, take the square root of the whole thing. And I get that this pendulum is going to be moving at 1.33 meters per second at that lowest point. So 0 speeds up to 1.33, slows down to 0, speeds up to 1.33, speeds back up. This, again, if you recognize this equation, remember v squared equals v naught squared plus 2ax. Well, if it's a gravity-controlled problem, if you only have kinetic and potential energy, so a would be gravity, but x needs to be not the path length, it needs to be the height change. But this works because gravitational potential energy only depends on height. It doesn't matter that this is this curved path or that other curved one. So I am going to make another video. I don't think I told you to take notes on it, but I'm going to make another video for the next assignment where we will have outside work done. But for right now, we're going to stop with only conserving mechanical energy, no outside work done by people or by friction. So that'll be all the problems tomorrow.